So this lecture is about indirect indicators of paleo earthquakes. So we've already talked some about these, but basically here we're talking about indication of intensity or acceleration at a point rather than actual faulting. But we attribute the acceleration or intensity to faulting somewhere. It's just we don't always know where. So what I'll cover is precariously balanced rocks. I mentioned already dendroseismology, lichen dating, and then liquefaction. There's been some questions about that, and then subaqueous seismites. And again, much of this comes from McAlpin. So here's the first one. So one of my students, he worked on these precariously balanced rocks, and the idea is that they're negative indicators of strong ground motion. So you can imagine if there was a big earthquake, if there was shaking, this thing would fall, right? It just can't. And same with this one. And same with this one. So that's why we say precarious, right? Because it's just unstable. And so, and they can be used quantitatively, or they're attempted to be used quantitatively to try to estimate what acceleration would require to topple them. And so if they're not toppled, then that tells you maybe we haven't seen that acceleration at that location for some time, and the time it takes to make a precariously balanced rock. So what I just said is tricky because we don't know, and the geochronology of precariously balanced rocks is still an area of research, but people use cosmogenic methods to date them. But in general, we think they take thousands to tens of thousands of years to develop. So the fact that it's there implies low rates of strong ground motion. And so this was an idea that started about maybe 10 or 15 years ago by Jim Bruin, who's a very famous seismologist, and he was driving around in the desert and he kept looking at these things saying, hey, that can't be big earthquakes if we see that. So after a lot of work, he tried to show these blue stars show the locations of precariously balanced rocks, and then the brown and red shows the seismic hazard for California. So expected peak ground acceleration. Well, it's the 2% probability of exceeding this number in the next 50 years, so 1G. And so what you can see is generally the blue stars are not in the brown areas. So it's not perfect, but we tend to see them better outside the main fault zones. And so what that means is that within the main fault zones, there's too often big earthquakes, and so they get knocked over all the time. So, David, one of my students, and then you see Olaf, the independent, the crazy one. No, everyone's crazy and independent, but so David, he worked with all of us to basically develop a simple way of studying these precariously balanced rocks. So here you see, there's his wife there, and she's working with him on this project. And here's the rock, and then here's the pedestal. So the pedestal, the interaction between the rock and the pedestal is kind of what controls its stability. And so the way that they look at these is you have some center of mass, and then there's an angle between the center of mass and what are called rocking points. And so what you want to have is large angles between the rocking points, because that means it's stable. But you can imagine if your rocking point is close to the mass vector, so in other words, the alpha, the angle between the line to the rocking point and the vertical is small, that means it's very close to wanting to tip over, right? But it's hard to measure that. So what we came up with was this simple method using photographs. So here's a map of a precariously balanced rock. And so the idea is you find the rock and you look at it, and you can then this is like a folding line, so we can look at the cross section in this plane. And there's one view of the precariously balanced rocks, or you can look at this plane. So you just line up and you take a picture kind of straight on. And then in MATLAB, so that's where Olaf came in. He's a really good MATLAB GUI programmer. So he programmed it so you could load the picture like this one, and you just click the outline of the PBR, precariously balanced rock, and then the MATLAB computes the center of mass because it's just the centroid of the polygon. And then you also click the two rocking points that you know here and here. So then it will figure out the angles for you. So it's just doing some basic geometry, but it's pretty fast because before everyone was trying to do really complex 3D models of the rocks, and it was kind of slow. Whereas now he could go in the field and take, a couple pictures, GPS, move on, a couple pictures, GPS, move on, so he could get hundreds of PBRs. And so instead of having a single measurement of the minimum alpha, so in other words, it's called a fragility, you could get like a probability distribution. And so this one place where he worked, looking at a bunch of precariously balanced rocks, he could see that this was the distribution of the minimum alpha. So you look at whichever of these two angles is lower, that would be your alpha min, because that's the one that's going to control its stability. And so here, this place, most of the rocks were pretty stable because the minimum alpha was close to 30 degrees. So, and that was in a place, because he could use it to look at the inventory of PBRs as, just how fragile are they, so how sensitive are they? So really, this side here is the most sensitive side of the curve because these are the really unstable ones. If you have if this angle's almost zero, that means that this rocking point's right here. So it's just, like the wind could blow it, knock it over. So anyway, he developed this method, and it now lets us study many precariously balanced features in an area and start to compare. So that's what we want to start doing in the future, is finding PBRs out here in low areas and looking at their alpha distribution and then coming in close to the fault. And the hypothesis would be that where there's recent earthquakes, many of these really fragile ones will be gone. And where there's not many earthquakes, we have a lot of them. So so that's something we've done with these features, which are excellent indicators of paleointensity. So moving on, we talked about dendroseismology, so you guys now are experts. So remember this, these trees were not on the fault, but they felt the fault, the shaking from that earthquake, and they were injured by it. So their growth rates slowed down. So here's another example. This is from New Zealand, South Island. And so Bill Bull, so the same guy who did a lot of the tectonic geomorphology, he, in the 90s, became really interested in lichenometry. So remember we discussed these are the lichens and the diameter grows. And so he studied more than 5,000, he made more than 5,000 measurements all over the South Island of New Zealand. And then he made sure it was the same species of lichen and roughly the same environment. So roughly the same weather, same elevation. And so then what he tried to conclude was that these peaks were times when major rock falls occurred, because he's mostly measuring the lichen on boulders. And so these clusters of lichen diameters mean that they're all the same age. And so by his calibration, he said, well, these that are, 9 millimeters in diameter come from 1968. And that was a big earthquake in the South Island in 1968. And so he had the idea that these rock falls were driven by the shaking from that earthquake. So then he finds another 1948, 1929. So these were known events. But then he goes back and he sees more peaks. And he starts to say, all right, well, these are probably paleo earthquakes. But somewhere on the South Island, he doesn't know where. It's not the same fault every time. It just means that it was shaking sufficient to drive the rocks out of the mountains down to the valley. So this is an interesting idea, and in a way very clever, because it's just looking at lichen. It's pretty easy to measure the lichen, but maybe gets a pretty good earthquake record for the last few hundred years. And also the other reason why this is interesting is that it's an intensity history, which maybe is good for seismic hazard, because people and buildings, they only get affected by shaking. They don't really get affected by ground rupture, because usually we know where the fault is, or it's such a small zone, whereas everyone lives around the fault. So if you want to start thinking about hazard, one way to do it is just look at how often does the ground shake a lot from multiple sources. And so that's how this can be used also. So I just had the one slide on lichenometry. I'm going to move on. So this one is then, we've been talking occasionally about liquefaction. So here it is. So this is an example of one of these. So it's a little, looks like a volcano. So what happens is that the ground shakes and there's a subsurface saturated layer, especially of sand, and the shaking of the ground transiently, so over just a short time, increases the pressure because of the shaking. And so that pressure causes an eruption. And so that's what we see here. And so here's an example where you see this means the water table. So this is saturated sand. And it's kind of, it's also has this weight on top of it from this superficial layer. So it may have already a bit of pressure, and it might be a spring here, or some kind of shallow groundwater. But when you shake it, you increase the pressure transiently, but you also decrease the strength of the cap rock. And so we can get that eruption to occur. So it's going usually up in a crack in the superficial cover. So even this, you can see these guys are in a line. So there's probably a dike that's feeding that line of volcanoes. So here's another case where this one was a lateral spread, where there was some kind of unconfined zone, and this sequence of blocks moved to the right, and so they caused extension between them and allowed for the opening. But here's a case where we just shake the material. This back and forth oscillation increases that pressure in the subsurface, but also provides some opening, and we get this intrusion and then extrusion of the sand. So here's some more detail of the geometry. So here you see the liquefied sand layer. It has this means the shear stress that's applied due to the shaking, the differential shaking. So this is what increases the pressure transiently. And so then here it's erupted. And so this pressure is enough to drive the sand up and out. And so here's what it shows is that for a well-sorted deposit, the sand is really the best material, and gravels and silts are less likely. And then this just shows if it's a little bit less well-sorted. But again, we see that it works best if you have a good, well-sorted sand in the subsurface that is saturated. Then it can liquefy easily. So, any question about the basic theory before I show an example? So let's look a little bit more. Look at that. So here's an example of paleoliquefaction, except that we know historically this earthquake sequence occurred, and it's in the middle of the continent in the United States, and it's a place where there are many pretty flat-lying sedimentary units, mostly sandy, and it's a humid temperate climate, so it has shallow water tables and not so much heavy vegetation, because the vegetation will give a lot of root strength, so it may be hard to break through heavy rooted zones because the cohesion of the cap rock will be too high. But this shows, so this just is kind of a geologic map where the hatch is the upland area. So the big river, the Mississippi River, goes here. It's a very large, low gradient river, and in this dark gray is alluvium with recognizable sand blow deposits. More than 1% of the area is sand blows. So it's a big area with sand blows and sand volcanoes. And in that same area, 1811 and then 2 in 1812 were 3 earthquakes. There's some debate about the magnitude, but more than magnitude 7 in this earthquake sequence. And so the interpretation is that these earthquakes shook the ground enough and the conditions were right along the river valley to produce significant sand blowing or sand eruptions. And so here's an air photo of that region. This is 1959, so it's still 150 years after the earthquake. But you can see all this white, all those white dots are the sand blows, and the alignment shows the dikes that fed them. So it's really amazing to see all of this still exposed at the surface. So these were studied, and then they used them actually to do paleoseismology because we could see the sand blows in earlier times as well. So this had repeated in the past, and there was no ground rupture associated with these earthquakes that anyone could find. So it's the only way they could be dated. So here's some examples of things they saw. So they'd have this source area where this underlying, you see it's kind of an aeolian or clean sand. Not aeolian always, sometimes fluvial, but clean. And the cap rock is above, and then here would be this dike that feeds the volcano. And this, you see the basal zone will have some entrained material that it rips off the sides of like just a regular volcano. It tears material off the side. And they note the black is I think organic material. So these upper cap rock is organic rich, almost like a soil horizon, full of, there's plants and also organic material. And so it's this material that gets ripped off the wall and entrained and then deposited at the base of the volcano, but more sand keeps coming, and so the eruption continues and builds the structure. So this is a classic volcano. You can see it's sometimes 10 meters wide, sometimes as much as 40 meters wide, so they're really big. And here's one that's a little bit more complicated. It doesn't have such a great vent, and it's fed by shallow distributed cracking because it found zones of weakness in the soil that that basically allowed the dike to go into multiple pathways. So this is thick sand. It says going down to 30 meters depth. So excellent conditions to make these layers. And then this is 2 to 8 meter cap, silt and clay. So you can push pretty far, especially 8 meters is a long way to push sand, but gives you a sense. So here's a more complicated one where it looks like, again, a complex magmatic system, but it's a magma of pressurized sand. And so you see its source area here, it erupts, and it intrudes entraining some of the country rock, which is this clay silt. Some bedding parallel intrusions are the sills, and then it cuts through the harder, the more cohesive clays. Going up again, another sill. This one shows lamination, so it might have been pretty water rich. It was actually more quite fluidized. And then this one comes up, and it in this case, because there was not a strong cap rock at the surface, it's just sand going into sand. And so it doesn't develop a good coherent dike that goes to the surface, so it just kind of dies into the sand. So the layering helps control in the final morphology. So if we'd had another stiff clay right at the top, it might have punched through to make a little volcano or blow, but it didn't. So here's some examples of what they can see, although this is not a great picture, but here's the injected sand dike coming up, and then it's a sill here, and then this, you see the laminated sand going in. So it was the pressure, the water pressure is high enough to really lift the rocks and keep them open, and maybe to pump sand and water to give lamination. So transient pressures are pretty high because this is a meter down. So if you can imagine lifting a meter of clay silt, it's still pretty heavy, right? It must weigh a few kilos. So the pressure is quite high, but it's being shaken at the same time. So some of the dynamic ground motions might be helping to lift these things open as well as the water pressure. So let's see what else. So that's the end of this topic. I have one more to show. Okay, so sometimes if you're in a lake or in the ocean, along that interface of water and sediment is an excellent mechanical boundary that often gets heavy shearing during an earthquake, and we have soft sediment deformation. And so we see flow features and we see brecciation. And so I'll show one example from my own experience, and then I'll show one of the most important papers on it. So here, you know, I've shown many times Central Asia, and this is near to where the Chun Kimin earthquake was, on the site of this big lake. So here's the lake is just around the corner. So when you drive into the valley, you see these flat terraces, and they're not river terraces, they're old lake terraces. And so there's many gravels, but then these light-colored materials are lake sediments. So every now and then the valley fills and the lake is higher, maybe because of a landslide at the outlet. And so it can be 100 meters deeper at times. But then it's not now. So we can go find these sediments and look at them. And so we went, and you start to see these kinds of features. So you see this distortion of the layering here. And then here's another one, this kind of hummocky characteristics. And then here's one, a big one by Chris. So when you first look at it, and if you know from your sedimentology courses or research, these are just generic soft sediment deformation. We don't know what caused it. It could be from rapid sedimentation, right, and water escape. That's the classic interpretation. But some of these are more indicative of strong shearing than others. And I'll show some of that next. But one thing that often is done is if it's over a wide area, you see the soft sediment deformation, then you start to interpret it as an earthquake, because the sediment loading type features would be more localized. Usually you send a deposit out that might only be 100 meters wide. But if you have tens of kilometers of the same levels showing the same soft sediment deformation, we think, okay, that larger wavelength of the signal is probably associated with a long wavelength thing, like an earthquake that shook the whole basin. So that's the challenge of the interpretation. So here's basically one thing that is interpreted. So this is showing the evolution of deformation in a laminated sequence. And here's the shearing. So it's back and forth. And so the layers start to detach a little bit, and they first fold, but then if you keep going, they get torn apart. And so then you may see this gradation from brecciated to fractured to warped to undisturbed. And usually then the indication is that the increased damage is right at the water sediment interface. So now if you add more sedimentation, you'll bury this horizon and the record will be preserved. So here's some other examples of these soft sediment deformation, which may be associated with shearing of that interface. So the biggest one is the brecciation down here, but light oscillation can cause these waves. You can have asymmetric billows, coherent vortices, and so on. So, at the base of the lake or at the base of the ocean, it's very fine-grained material is water saturated. It behaves almost like a fluid, but it has a higher viscosity than the water. So here's the maybe most famous use of seismites. It's from these colleagues from Shmulik Marko. He was his PhD, and they're working along the Dead Sea Fault in the Middle East, and this is a left lateral fault that lets this block, which is like the Jordan block, move to the north relative to a fixed Sinai block, or this is called Arabia and Sinai. So you see left lateral, and in the middle of the fault zone, the valley, is this water body that's called the Dead Sea, and it's connected to this one called the Sea of Galilee. And now they're low, and it's a desertic place, high evaporation rates. But at earlier times in the Pleistocene, when the climate was wetter, it was one single big lake that went all the way from south of the Dead Sea to the Sea of Galilee. So it filled the fault valley of the Dead Sea Fault. And so it was much deeper. And so this lake was called the Lake Lizan. And so in this place, there are sediments associated with the Lake Lizan called the Lizan Formation. So they're lacustrine laminated silts mostly. So these guys looked at the stratigraphy and they found many, many of these soft sediment deformation features in the Lizan Formation. And they started seeing things like this, where there was actually faulting, and then this mixing, and then also deformation. And so when they say mixed layer, this is what they mean. It's this kind of folded, but then also brecciated layer. So the interpretation is this was the bottom of the lake and top of the sediment at the time of some event, which was a strong shaking event. So they looked through all the stratigraphy. They saw other features like this one. And so this is a fissure that formed due to shaking. And basically the clay-rich lacustrine units have some cohesion. So if you shake them enough, sometimes they just break open and a crack opens on the floor of the lake. And the varves means fine lamination. And so material falls in, but then it gets buried. So they had many mixed layers. And so here's an example where they would have the lake. Sometimes a fault would occur in the lake, but not always. Sometimes it was just shaking only. And there would be liquefaction at that level. Some sediment is suspended in the lake. It's dusty, basically, or muddy. And it would be deposited. And you would bury that scarp back with more sediment that's undeformed until the next earthquake occurred. So this was impressive because then they could get a huge record of earthquakes for thousands and thousands of years, because the title shows 50,000 year record of earthquakes. But the important thing is that they don't know what fault. They just know that there are a few faults cutting through their unit, but these are these kind of secondary faults here. But more, they assume that these are even sympathetic, kind of driven by shaking due to big earthquakes on the Dead Sea Fault, because the Dead Sea could generate magnitude 7 plus earthquakes. So they came up with some interesting clustering. So they showed that, in this period, 25,000 to 35,000 years ago, there were many earthquakes. And then, so number of earthquakes for a 5,000 year section, as many as 7 in one 5,000 year period. So rapid, like recurrence less than 1,000 years. And then there was a pretty quiet time where there may have only been one earthquake in a 5,000 year period. Then it goes back up to as many as 8 earthquakes in one 5,000 year period and down. So it shows the complexity of the earthquake recurrence, that it's just not one every 600 years or something. It's quite variable. However, it's also just intensity. So it just really is saying shaking at a point had this clustered behavior. But, you can imagine that if you're over here, like in my head, and there's a fault here and a fault there, and I'm equidistant from both faults, this one can have an earthquake, and then this one can have an earthquake, but where I am, it has the same amount of shaking. So we get 2 records of earthquakes, but it's not telling me about the recurrence behavior of this piece of the fault. It's telling me about the overall recurrence behavior of all the faults in some radius around my head. At least for this place, though, there's not that many faults. It's mostly just one main fault. So it's a little bit simpler geometry, but it's still not uniquely telling us about earthquake recurrence on the fault at a single piece of the fault. So they also showed that they tried to show the time between the earthquakes, is what this is, the interval greater than. And so the frequency of intervals was plotted as a function of their length. So long intervals were rare, and short intervals were progressively more common. So they tended to see the most common interval was a short one. And so what I wonder is if some of this is an aftershocks. If you have an earthquake of magnitude 7, right away it has aftershocks, but it can have aftershocks for a few years. So what if you have a 6 a year later, so it's separated by some sediment, you record it, so it looks like a very short period. It might only be 10 centimeters higher than the last one. So this, in my opinion, is a really important paper, because it is basically nobody has a 50,000 year record of unique earthquakes that are occurring at a point. And so it's quite valuable, but it requires this special condition of these lake sediments to be preserved. So just to conclude, this is the last one. It tries to show seismic versus non-seismic. And, the sediment loading is one of these things that is somewhat ambiguous, where it can be sometimes seismic, sometimes not. Whereas over here on the side that's definitely seismic is these things like cyclic shaking, high pore pressure, vented sand features. These require the shaking. That's the only way to get that pore pressure high enough. Whereas we know other intrusive features like ice wedging or something might look the same after some time, but obviously isn't caused by seismic processes. So, but some of these in the middle here, like this water escape and warped and folded bedding, can be a little bit ambiguous. And then here you see your subaqueous slope failures, which is sometimes seismic, although you see they're leaning to rarely seismic.